we start with part 2, you guys have seen this. If f is continuous on the interval AB, then the integral from a to b of f of x dx is equal to f of b minus f of a where f is any antiderivative of f, and for good measure your book chooses to state this: f prime equals f. The derivative of that antiderivative would give you the original, so that should make sense. That's exactly what your book has written down. So the preface is that it must be continuous. Note that we talked about if you have a point of discontinuity, say 1 over x squared, that would be discontinuous at 0, so your integral, your bounds of integration cannot lap over 0. Are there any questions about the first one? You already know, yes, I'm sorry, the first one being part 2. You already know part 2. Are there any questions about that? Then let's look more intently at part 1. Part 1 says this: if f is continuous on AB so given a continuous function, then G is defined by the following. So what we're going to do now is we're going to take that definite integral, and instead of creating a definitive end, we're going to put a variable in for one that we are going to use to change it. This is basically what it's stating, you guys. You could take this area, this definite integral, and you can write it so that it's a function of changing values. And if it's a function of changing values, it has some interesting aspects about it. We are not going to do a whole lot with it, but there are some things that you should see. So G would be defined by the following: G of x would equal the integral from a to x of f of t dt. We choose to use a different variable because x is what we're going to substitute in. I don't want to write x twice. So that's a function. It's an area function. It generates area for us. Whatever we change x to be, it's going to give us a different output. Given a is less than or equal to x, which is less than or equal to b, so x is somewhere between that interval, it will create function values for us. B is going to be like the end of the interval, the last spot that we could evaluate. Note, we're going to run x from very small to very big. We're going to change its values. And I'll describe that graphically here in a second. So we'll put it down graphically and relate it back to what we state. And this last part is important. G is continuous on AB. So that's important. And differentiable on AB. And G prime of x equals f of x. Differentiable. It's able to be derived. You can differentiate it. Yep, g prime of x. Yeah, you can't take the derivative of an endpoint. You could take a one-sided derivative of an endpoint, but it would have to have the other side truly to take the derivative. We're not going to get caught up in that, okay? The reason why we wrote it down is, for good measure, it's in your head. If you see it again in future years, you know what it is. But we're going to take our drawing and we're going to compare it to the language we wrote so we can understand exactly what's happening. Are you ready to see the graph? Okay, so there was a question asked here already, I believe it was either by Kyle or Derek, in regard to the function itself. So if we call this f of t, and we define it from the interval a over to the interval b, and we're going to place x somewhere between a and b. So what we've said before was that we were just going to add up all the area from A to B, right? And that's what you guys practiced. And you can do that, right? We're all good at that. What this is saying is, well, let's state that, x could be a value between A and B. Obviously, if I move x closer to A, is the area going to become smaller or bigger? Smaller. And if I move x closer to B, will it become smaller or bigger? Bigger. That would change if the function went below, say, the x-axis. And so we'll watch and we'll see what happens with that. So if you want to define g of x is this part right here. G of x is equal to the integral from a to x of f of t dt. So, you're used to seeing a function as a graph. I would like to draw a graph of g of x. I can't really do that yet. And we'll do it with an example to come. But right now I want you to understand that this function is what we would refer to as the area function. And there's a relationship that exists. Specifically, you should note that if I take the derivative of g of x, if I take the derivative of my area function, do you know what I get? I get that function, f of x. X inserted for the variable. Instead of t, we replace it with x because we're defining it at that spot. What that means is the rate of change of rate of change is a phrase we use to describe what? Slope or derivative. So the derivative, rate of change of g of x, and g of x is the area function. So the rate of change of the area function is f of x. Whoop, sorry, if is f of x. Any questions? Okay, let's go to a concrete example. All I did is I took what's up there and put it on a graph down here so we can understand it. We would like to take x, we'd like to move it to the right, to the left. We'd like to take x, we'd like to move it to the right, and we'd like to see what happens with the outputs. Let's consider this example here. We'll define g to be the area function bounded from -6 to x. We'll call it over the interval of -6 to +6. You could write that down. And this function here we will call f of t. So I'm going to say that g of x is going to be the area function. The first question is, it says evaluate g of -6. If g is defined to be that, I want to find the area from -6 to -6. What's the area from -6 to -6? Nothing. Now I'm going to find the area bounded between the function and the x-axis from -6 to -4. Very good. 2. So you see that we're giving it inputs and it's giving us outputs. So we've always just come up with one answer. Well, if we just change x or the boundary, obviously that's going to change the results. And this has an interesting dynamic with it. G of -2. I have this 3. And then I have, I'll draw it in green, I have a little bit of positive and I have that same amount negative. So that positive and that negative will cancel and I will simply have a value of 3. Okay, so the area above and the area below in that situation will cancel. Now, how about all this area here? That's all negative. So we know that the green's canceled. Now it wants us to add all the way to 0. So I have this stuff here. How much would that be? I think that's, if you put that rectangle there, that would be -2. And then another -3. That would be a total of -5 more. So instead of 3, we'd have -2. Yep, just by coloring. So our previous value is 3, and we added -5 squares onto that. So we got -2. Okay, now I want to go up to 2. So the integral from -6 to 2, how many more negative squares get added onto that? -6, so that will give me -8. No. Again, you know, you would always, and if you were told in geometry that area is always positive, that's correct in the way that you think about area. But area in this situation, we can represent it as the definite integral. And so we will talk about net area, and so we'll create both as positive. But again, this could be, say, revenue. This could be cost. And as you figured out, you would have a loss instead of a profit, right? So, you know, that's part of the application that it can move towards. Not in the sense that you've always thought about, no. Okay, so I'm going to add on more negative area. How much is this stuff right here? I'm going to add on this amount. I'll do it in green. This is a -2, and then I have this sliver that those cancel out, right? So I just have -2 more that I'm adding, and that will get me to be at -10. And then I'll go all the way to 6. So I'm going to add some more area there. This will be another 2 units. And then another 3 plus 2. So looks like I've got 3. Well, I've just got 1 there, so 4. I've got 2 there, so 6. So if I add 6 onto that, I get -4. So if you just count the boxes, that will give you, a general idea. So these are our table values. It says on what interval is the area increasing. So starting at 0, as I move to the right, is the area increasing right away? Yes, it is, until I get to what value? -2.5, right. So the area is increasing from -6 to -2.5. And then we noticed it go down for quite a ways, didn't it? When did it start increasing again? When I hit 3.5. So it's increasing from 3.5 to 6. So in other words, it's increasing wherever I have area above the x-axis, and it's decreasing wherever I have area below the x-axis. So it's going to be decreasing from the interval negative 2.5 to 3.5. Are there any questions how I came up with those values? Okay. Where does g of x have a minimum value? Think about it, you guys. G is the sum of the area. If I start at negative 6, okay, if I go from negative 6 to negative 6, what's the area right away, we said? 0. Does it ever go below 0? Yeah, so we know that that's not a minimum. If I go up to this spot, negative 2.5, is the area positive or negative so far? It's positive. Somewhere over here it dropped to negative, didn't it? And it continued to be negative, more and more negative, more and more negative until I got to 3.5. That's where the negative area stopped accumulating. You can see I'm continuing to add negative area until I get to 3.5. See? It was decreasing from negative 2.5 all the way to 3.5. So it's decreasing. Then it starts to finally go up. Okay? Yes, finally where it starts to change from down to up. So your minimum value. Yep. Now it says sketch a rough graph of g of x. And so all I'm going to do is I'm going to take those points and just plot them and see how they match up with this. Okay? So negative 6, 0. That's one spot on my graph. Negative 4, 2. That's another spot on my graph. Negative 2, 3. G of 0 is negative 2. G of 2 is negative 8. 1, 2, 3, 4, 5, 6, 7, 8. You can draw tick marks. G of 4 is negative 10. And then G of 6 is negative 4. Now, we could talk about whether or not these lines would be straight or they would have a curve. They do happen to be straight, and there are some other points we could add in. But again, it says sketch a rough graph. It would be fine to just, do one of these things. That's a rough graph. Again, does it look like the minimum value is somewhere around 3.5? Sure it does. Okay? And so that would be the graph of g of x. Oh, look at that. And I was hoping it was for me. All right. Okay, so you're going to have a question or two on your assignment where you're asked to do this. Everybody okay here? Okay. Let's do... What was that? You should know how to do an example like this. So, now let's do something that's going to come just a little bit more natural to you. It says, use the FTC Part 1 in order to find the derivative of the following functions. Now remember, we said that g of x was equal to the integral from a to x of f of t dt. And g prime of x was equal to f of x. Boys, so this is the relationship that we want to set up, and this is going to be really straightforward, okay? Watch what we can do. Oh, I'm sorry. Instead of the t, that should be an x. Keep our notation the same. I want to take the derivative of g of x. So look at what changes, everybody. It says g of x is equal to that. If I take the derivative of g of x, I get rid of all this area stuff. I'm just left with f of that. The only reason we switch the variable is just for a substitution purpose. We are just you will see exactly why when we do example 5. It will come clear at that point. Okay. Okay, so once again, if you want to take the derivative, what happens is it says if you take the derivative, here's what happens, Ella. We take this and we make it go away. We take this, we make it go away, and we plug that in there. So the idea is that if you take the derivative of the area function, you get the original function. Anybody want to guess what the next one is? Doesn't matter. No. I'll show you. Just watch. What's different about this? X is on the bottom. Here's a little trick. We can rewrite it. G of x equals the integral from 6 to x of I'm sorry, we'll put the negative out front. Doesn't really matter. Negative sine of t squared dt. So what happens is if you had the x on the bottom, it switches the value to negative. So we talked about that yesterday. Remember when Greta plugged it into the calculator and she got the negative value? That's what happens. So now I can plug it in and I get g prime of x is equal to negative sine of x squared. That's it. Natural log. So g of x is equal to, we could write this as negative integral from 3 to x of natural log of t dt. And again, derivative and area are like inverse operations. This is what it's teaching you. Just like if you take 1/2 times 2 on the x, those go away. You know, inverse operations. We're doing the same type of stuff. So if you want to make area function stuff go away, just take the derivative of it. And in this case, we get negative natural logarithm of x. That's it. Okay, right. Marlene says this is way too easy, so we're going to introduce Kelly's question, which is why the t, so we can understand it just a little bit better, because now, just watch. This will make sense to you, okay, but this is confusing. If you don't watch this, you won't get it, I promise. So if you're playing with a, oh, I thought you were playing with the camera, Ben Jones. All right, so what is the rate of change? What's the derivative of x? The derivative is 1, okay? What is the derivative of 2x to the third? 6x squared. It's not just 1. And so you learned that if you were to see something like sine of x squared, you can't simply say it's just, you know, the derivative is cosine of x squared. You have to use a very special thing that we learned first semester called the chain rule. And it trust me, it's not bad. Watch it happen, okay? This is all we need to do, okay? We just write this function down, okay? We have the area. We'll just call it from 1 to t. We're going to use that as our substitution variable of t squared minus 1. I'm setting up my graphic organizer here. Okay. Yep. I use my substitution, or my inside piece is 2x to the third. Remember, this isn't so different. We would use cosine of u, and we would use 3x, and we would take the derivative. We would get, negative sine of u, and we would get 3, right? So we're using two different variables to help us. The one is a substitution variable. The other one is not. Yes? We're going to plug that back in there. Just like we switched this to a u. Sure. Yep. Shh. Boys, please. Okay? So, if you take the derivative of this, okay, what goes away? The area part goes away, right? And you're just left with this. T over t squared minus 1. What do you, if you take the derivative of this, what do you get? 6x squared. Now, no. Remember, the chain rule says you take this times this, but you have to substitute this back into those spots. X to the third back in. 2x to the third here. I get 4 x to the sixth minus 1. I got to multiply that by 6x squared. And I get that's it. Yep. So we just set up the chain rule. We're going to do it one more time, and I promise the second time will be easier. Can't reduce parts. Nelson's already cut off 3 fingers this morning. Okay, what's the first thing you notice about this one? Good. If you flip it, then you get g of x is equal to the integral from 2 to 1 minus 4x, and this negative will then turn positive. So I have the cubed root of sine of t dt. Okay, again, the derivative of this is not 1. It's not simply just an x. What is the derivative of this? Negative 4. So this is a chain rule exercise now. So go ahead. This one, because we flip these values to get x on the top, it switches it to a negative value, which will cancel that one out. This one, you can put it on the outside or the inside. So this one I applied the negative to the outside, and it carried right on with it. Okay. All right. So we write it out. Here I have the integral from 2 to t, cubed root, sine of t, dt. Yes, you could really put any variable you want there. It's a substitution variable. Here we put 1 minus 4x. Now we take the derivatives. When I take the derivative of this, what goes away? All the area stuff that we talked about. And what you're left with is just simply the cubed root of sine of t. What's the derivative of 1 minus 4x? Negative 4. So what we have to do is take this and plug it in and multiply by that. if we multiply these together, I get negative 4 times the cubed root of, and that's it. So see, it looks confusing right away, but it's not too bad. So on your assignment, you guys, you'll have a couple that are, just basic. You just remove the area stuff and you're done. You'll have a couple where you actually, you need to switch them. You'll have a couple where you need to use the chain rule. So you have, for those of you who are here tomorrow, you can work on this. I have this content included in your study guide as well. So there's a lot of you who will be around. We will do nothing new tomorrow. If we need to review this again on Monday when you guys get back, we will. Question? Yes. This is the last assignment you receive before your test. That's it.